Hello everyone, welcome to my Your Programming Club. Today we will be solving another daily LeetCode problem, and the problem's name is maximum number of moves in a grid. Okay, so the problem statement goes like this: you will be given a zero indexed m cross n matrix uh, represented by a grid, okay, consisting of positive integers. Okay, and you can start at any cell in the first column of the given matrix or the grid. Okay, and the and traverse the grid in the following way. Okay, so from the current row or column that you would be selecting from the from the current cell, from the first column that you would be starting from, you could move to any of the adjacent cells. Okay, and those adjacent cells are these cells. Okay, so if you are considering this as your current cell, okay, so you can move to either of these cells. Okay, so diagonally up, okay, and diagonally down, or towards right. Okay, so any of these three directions you can move from the current cell. Okay, so these are the three directions in which you can move into. Okay, these directions. So the value of each cell you move should be strictly bigger than the value of the current cell. So this is also needed to be taken care of, that if for example here you are at 4, okay, then if you are moving to 9, 9 should be strictly greater than 4. Okay, so you have to return the maximum number of moves that you can perform. Okay, so let's say that you started out from this particular cell and you made the first move, then you made the second move, and then you made the third move. So in all these moves, uh, 2 is strictly less than 4, 4 is strictly less than 9, 9 is strictly less than 11. Okay, and in total 3 moves were made. Okay, so this would be resulting into 3. So as you can see, the 3 is the output. Okay, so this is what you have to do. You have to return the maximum number of moves that you can make. Okay, following the constraints or the rules of the traversal that you would be you are given in this problem. Okay, now before thinking of an approach, let's have a quick look at the constraints. So according to the constraints, uh, see the length and the number of rows and the number of columns of this particular grid is of order 10 raised to power 3. Okay, and the number of cells m cross n is of order 10 raised to power 5. Okay, and each entry in the grid would be of order 10 raised to power 6. Okay, so these are the constraints. So let's quickly try to think of an approach. So if we try to do it the brute force way, then for that particular case you would have to for each of the cell there would be three possibilities of going in three directions, three different directions. So if you are wanting to try out all possibilities that are there, then 3 into 3 into 3, and it would be repeated into number of cell times would be the number of order of operations that would be required for your brute force solution. By your brute force solution, basically it can be considered as a loose upper bound. Okay, so a loose upper bound can be this number of operations, and there is a operation limit of 10 raised to power 8 operations. If the number of operations required by your solution to solve a particular problem exceeds that particular limit, or it even reaches equal to it, then you may get a TLE, and TLE is basically time limited exceeded. Okay, and your solution will not be getting accepted. So you need to do the optimization in the brute force approach that you are taking. Okay, so now we will be seeing what optimizations we can make, and before that we will be making couple of observations. The very first observation is that this problem statement is following the property of optimal substructure, and if you are hearing this term for the very first time, link of this particular property would be provided in the description box, so please make sure you definitely check it out. So what happens is, let's say you are at a particular cell, and the coordinates of that cell are R and C. Okay, so what would have been previous cells from where we you from which you could have moved to the current cell. Okay, basically you are considering this as your current state, and what would have been the previous possible states from where if you would have made a move, you would have landed up on the current cell. Okay, and those cells are these cells. Okay, diagonally up, diagonally down, and the left cell. Okay, so this could have been the previous cells from where we could have landed up on the current cell. Okay, so uh, you see that there are two state variables on the state on which the state is currently depending upon the whole process of finding out the result where you are at depends upon the two variables only, which is the row and the column of the current location, or basically the current cell. Okay, so a 2D structure would be sufficient to store the current state and the previous state results. So I will be telling you in a bit why we would be storing those results. But you see that they are dependent. The current solution of a bigger problem is dependent on the solution of the smaller sub problems. Okay, so in a way we can say that the solution of a bigger sub problem can be found out by combining the solutions of smaller ones. Okay, so if we are referring the current state, or if we are finding interested in finding out the maximum moves at the current cell R and C, so we would be requiring the contributions from the previous states. So we should be knowing that, and if we know that, then we can build the solution of the current state. So in a way we can say that solution of a bigger subproblem can be formed or found out by combining the solutions of smaller ones. Okay, so the next observation is link of this particular one will also be provided in the description box. Okay, so you can definitely check it out. So the next property of this particular problem is overlapping subproblems. So see, let's say we are using recursion to solve this particular one, and let's say we are using a combination of steps to reach to our final cell. Okay, and let's say this is our final cell as of now. So see, in these two combinations, this much portion is common. Okay, so you would be doing extra work to recalculate or do recomputations for this particular overlapping part of two different combinations. Okay, if you are using a recursive kind of approach. Okay, so this kind of extra recomputations or extra work can be avoided if you just store the results of these kind of subproblems and use those results whenever you encounter those subproblems again. Okay, and this or occurrence of the subproblems again and again in different combinations is called this overlapping subproblems property. Okay, and basically if a problem follows these two kind is having these two kind of properties, optimal substructure and overlapping subproblems, then a optimization technique can be applied here, which is known as dynamic programming. Okay, basically and before proceeding, if you are hearing this also for the very first time, then please head over to the description box and a link for this particular one will also be provided. Okay, so I will be describing in a nutshell what it is. So basically you store the results of the subproblems so that if they occur again in some different combination, then extra work or extra computations can be avoided. The second thing is that you build the solution of bigger subproblems on top of the solutions of the smaller subproblems. Okay, that you have already seen. Okay, so these two things we are doing in dynamic programming, and now we will be seeing how we have implemented this approach. Okay, so as we discussed that our current state, let's say this is representing our current state, would be dependent on two variables, the row number and the column number. So we would be using a 2D structure to store the solutions of the problems. Okay, so a 2D dynamic programming structure or a 2D array would be sufficient for that. Okay, and it is mentioned in the problem statement that you can start at any cell in the first column. Notice that the first any cell can be chosen as the starting point in the first column. So that is why we are saying that uh, we are also considering the first column as the as a move also. Okay, so basically we are storing one there, since we are supposed to start from the any cell in the first column. So we are marking all the cells in the first column with one. Okay, so that it would help us to take contributions from the previous states. Okay, and let's say you are at a current state, then there would be three possible previous states from where you could have ended up on the current state. That is left upper diagonal, right down left down diagonal, and the left cell. Okay, from either of these you could have ended up on the current state. Okay, so what you would be doing here is, since you have already covered the first column, you would be starting from the second column onwards. Okay, and for each of the column you would be doing the following. uh, Basically you would be doing a column measure traversal. So since the current state is depending upon the previous columns. Okay, so that's why we are using a column measure approach. So uh, basically for each of the cell or the current state. Okay, let's say this is the state that you are trying to find out. Okay, maximum moves at this particular cell. Okay, so you would be taking contributions from the previous possible states. Okay, and those previous possible states would be these three. Okay, as I have shown here. Okay, and you would be taking their contributions. Basically whatever number of moves were made till here, it would the moves number of moves here would be just one more than that. Okay, so this is what we are doing. Okay, after making a couple of checks. Okay, the very first check is that we are well within the boundaries of the grid, and it is possible first of all to have may been here. Basically if you could not have been at this particular cell, then what is the use of taking its contribution? Okay, so this is what we are doing by making this check. Okay, in all of these three possible previous states. Okay, so it should be definitely greater than 0, otherwise we would not be taking their contributions. Okay, and then once you have taken out all the contributions of the previous states, and then you would be taking maximum of them. Okay, because we are wanting to maximize the number of moves that can be made. Okay, so that's why we will be taking maximum contributions from the previous states. Okay, so once you have found out the current state maximum moves. Okay, which is the number of maximum moves possible at the current cell. Okay, then you would be updating your maximum moves. Okay, maximum number of moves. Okay, and we would be subtracting one because we were considering the starting point also in our moves, so we should be subtracting one because of this particular thing. Okay, and then once you are done with all these, you have populated your maximum moves array. Okay, then you would be returning your maximum moves. Okay, that you would have stored. And this is the whole approach and the implementation. And as far as the time and space complexities are being concerned, the time complexity wise, if let's say there are uh, R rows and C columns. Okay, so there would be a total of R into C cells. Okay, and so time complexity would be R into C. Okay, and since we are using a 2D structure to store the states of all the cells, and it is a 2D deep array, so space complexity would also be the same, R into C. So these will be the complexities, and this is the approach and implementation. If you are still having any kind of doubts or any queries in general, then you can ask them in the comment section. And I really hope this solution walkthrough added some value to your journey of honing your DSA skills. Keep solving more and more problems, and I'll be seeing you in the next video. Thank you for watching.